Okay, here are my solutions. So the derivative of arc cosine is basically found the same way as I did with arc sine, except that this time the derivative of f gets us a negative sign in the bottom, and then we plug in arc cosine. Essentially the same technique as used with arc sine convinces me that sine of arc cosine is square root 1 minus x squared, so that's not different. Now for arctan, it is a bit different and a bit harder. Now, of course, we have the secant squared, but that's not so much the hard part as the arctangent is. So what does arctangent represent? Well, if this is going to give us an angle corresponding to what? What does the x represent? It represents the ratio of opposite to adjacent. Now, as always, we know that we're working in the unit circle, and the Pythagorean identity tells us this. Now, if we were to say solve, right, because we're saying that x is equal to that, so if we multiply both sides by the adjacent, then we could substitute into the Pythagorean identity. There's an idea. It seems to work out, because then we get to factor out the adjacent squared. And since it's all equal to 1, we can infer that by dividing by the adjacent squared, that 1 over the adjacent squared is x squared plus 1, which we hope will be useful. And the secant of this angle, because again, recall that the arctangent produces an angle, and we're taking the secant squared of it, well, the secant squared is just 1 over the adjacent, which, hey, fortuitously, is the thing that we derived earlier being equal to x squared plus 1. So now when we go into, what is 1 over sec squared of that angle, which is really what we found it to be, it's the same as 1 over x squared plus 1. So that's the answer. This is the derivative of arctangent. Okay. If f of x is this relatively simple function, find the derivative of its inverse. Well, simple high school methods produce the inverse of the function, and we can just straight away take its derivative using the methods we've talked about so far. If you're at all confused about how you take the derivative of this, you really need to bone up on those derivative skills, but the answer is that you just distribute the 1/2, and this is equal to x over 2 plus 1 over 2, and as you take the derivative, the x just turns into 1, so we get a 1/2 here. The divide by 2 doesn't really matter, and then you take the derivative of 1/2 and it's equal to 0. So all that you're left with is 1/2. So that's the derivative of the inverse function. We actually didn't need the theorem talking about the derivative of the inverse, but we could talk about it anyway if we want to, because hey, after all, we're on the theme. Then we could say that the derivative of the inverse function is 1 over f derivative plugging in the inverse function. What is f derivative? Well, if we look back up here at f, then the derivative is equal to 2. And it's the constant function 2, so you can plug in anything you want and it'll stay 2. So this is just 1 over 2, which is exactly the same as we found the other way. Okay, we'll find the derivative of ln of 2x by chain rule. We say the outer, the inner, we get their derivatives, we plug in the original inner into the derivative of the outer, and multiply by the derivative of the inner. After cancellation, the answer is 1 over x. Notice that we could have produced the same result just by using some logarithm knowledge, that it's equal to ln2 plus ln x. If we take the derivative of this just vanishes, turns into 0, and this is 1 over x, the same answer. Okay, here we will take the derivative of the outer, which is 1 over x, plug in the inner. I'm being fast about the chain rule now. So you just get 1 over x from the logarithm, right, f prime plugging in g. Then you multiply by the derivative of the inner, and after putting cosine over sine, you get cotangent. Taking the derivative of sine, you get cosine of ln x, that's derivative of the outer, plugging in the inner, multiply by the derivative of the inner, and then just algebra to tidy it up. Okay, here we take the derivative of the outer, plug in the inner, as always, and then we multiply by the derivative of the inner, which in order to calculate, yes, you need to use all those obnoxious trig derivative identities. But when you do, you get this. Notice that you can factor out secant from this. And when you factor out secant, you're left with tan plus secant, which is exactly what's on the bottom as well, so they cancel. And you're just left with secant. Okay, now the way that you should do this one is knowing that e to the x and lx are inverse functions. They cancel and just leave. This is just the same thing as the function x. So when you take the derivative, it's just equal to 1. But if you did it by chain rule, you should eventually get an equivalent answer. By chain rule, derivative of the outer stays the same, right? Derivative of e to the x is e to the x. Plug in ln x, multiply by the derivative of ln x. And again, you can, at this point, use the fact that e and ln cancel, leaving x. So this is really x over x, which is equal to 1, the same answer. Okay, here. I would say the best way to do this is to realize that you can rearrange this as 10 to the 2 to the x, and 10 to the 2 is 100, and now you can take the derivative using the fact that if you have a different base, you get this little obnoxious ln of the base factor, and times 10 to the x still. So if you did it by chain rule, there's this other derivation. Fine, I won't talk about that. Where are these functions defined? Where are these functions even differentiable? I haven't really talked about that, and I might go back and make more videos and insert them in earlier places, because I should have talked about the concept of differentiability. So this function is restricted to -1 to 1. So where is it differentiable? Not at the endpoints. It is discontinuous at -1 and 1. If you plot it, you will see that it is discontinuous on that interval. Or sorry, not on the interval, but at the endpoints. So this is not differentiable, right? If it's discontinuous, it's not differentiable, because you need the limit to exist. So, so this is not differentiable at -1, nor is it differentiable at 1. We could say similar things. This actually goes from -pi to pi and is not differentiable at the endpoints. And what else? Do we have any other interesting ones? I guess it is kind of also interesting to remark that the derivative is itself not, right? Even if you just looked at this function, it would, this function. It would not exist at 1, nor for negative numbers. So in fact, it sort of interestingly aligns with arc cosine in exactly that way. Anyway, moving on. The logarithm is not defined for 0 or negative numbers. Now, if we look at the derivative that we produced, in fact, we lost sight of this. This is kind of my fault. But this is the correct answer only where the logarithm is defined, which is namely for positive numbers. Whereas 1 over x looks like you could plug in a negative and get a meaningful answer out, but that's wrong. So in fact, this is only the correct answer restricting to positive x. So that's where this function is defined and differentiable. Here, sine is defined everywhere and oscillates from -1 to 1. So that means that, you can't be plugging in -1 to 0 into the logarithm. So you really have to restrict this thing to where the sine function outputs positive values. The most sort of obvious restriction that would accomplish that is to restrict from 0 to pi, exclusive. So here, with the rest of these functions, you largely do the same thing, right? This function is actually not equal to x for negative values. Again, by the same logic, you cannot plug in negative numbers into the logarithm. So saying that it's the same as x is actually a little bit inaccurate. It's the same as x when restricted to positive values. What many books do is they just talk about ln absolute x, and then you get to use negative numbers, but you still don't get to use 0. Anyway, I tend not to bother with that and just sort of restrict to positive values.